This simulation provides a crude model for a complicated device, the yo-yo. In fact, the dynamics of a yo-yo are complex, and we'll barely do them justice here. However, they provide a compelling way to think about a specific type of mechanics problem. Basically, how quickly does an object accelerate to the ground when rolling off a string? This type of problem is usually treated in more advanced classes, so we are presuming a lot of prior knowledge here. For instance, we're analyzing the torques acting on the yo-yo, and we're looking at how the rotational inertia, the rotational analog of mass, sometimes known as moment of inertia, acts to lower the acceleration of the device. Let's hit play and watch the yo-yo descend and return. As we can see on the graph at left, the downward speed of the yo-yo increases to a maximum, and then it rapidly comes to a stop. This is likely not physically terribly accurate, but anybody who has yo-yoed knows there is a feeling of jerk there when the yo-yo comes to a stop. It is also an excellent time for the string to break, as the forces acting to bring the thing to a stop pretty quickly are high. After the yo-yo sits spinning with zero speed but still some angular velocity, presumably the operator gives it a light tug and it returns upward, first quickly and then decelerating to a stop in his hand. If we watch the angular speed in the graph at right, we see that it increases to a maximum, stops when the yo-yo spins at the end of the rope at that maximum value, and then decreases back to zero as it rolls back up the rope. In order for the yo-yo to accelerate downward, there must be an unbalanced force. Let's show the free body diagram, or FBD, for the yo-yo. As we can see, there is an upward tension force and a downward gravitational force. The downward gravitational force exceeds the tension force, and this explains why the yo-yo speeds up as it travels downward, and then slows down as it travels upward. Notice that the gravitational force acts on the center of the yo-yo, and that it generates no torque about its rotational center. But the tension force acts off-center. This means the tension force is responsible for a torque about the center of rotation. The torque causes the yo-yo to spin up as it descends, then slow its spinning as it ascends. Let's show the torque and watch a full cycle of the yo-yo. First, we see the torque pointing out of the page, represented by a circled dot. Then we see the torque pointing into the page, represented by a circled X. You can adjust the rotational inertia of the yo-yo by changing its type or shape and its size. The rotational inertia is a measure of the matter content as well as the distribution of matter for the device. Objects that have more mass at higher radius will have higher rotational inertia. For these yo-yos, the torque due to the tension in the string will generate a lower angular acceleration, and the yo-yo will spin up less rapidly. So play around, try different throw speeds and yo-yo types, and see what you can discover. Thank you for watching.